Hello everybody, welcome to our webinar today presenting the output from the STERNA 2050 project. My name is Peter Stringer. I'm the Chief Technology Officer at Supernode, a company founded to develop the next generation superconducting power transmission technology. The European Union's climate goals require a rapid increase in power from renewable energy sources, and our current grid infrastructure doesn't have the capacity or flexibility to transmit this power, particularly offshore, where much of this power will come from. To meet our future needs, many more connections are needed using today's technology, or a major technological shift is needed. And that has been the purpose of the STERNA 2050 project, to explore how new grid technologies with special attention to superconducting cables can be implemented and how they should be considered. This project has taken its name from Sterna paradisa, the Arctic tern, a small lightweight seabird with the longest migration route of any animal in the world. Its route links different continents and climate zones around the world. And that's really what humans need to do with our grids so that we can deliver cheap, efficient, renewable power to everybody. Supernode have led this project, funded by the Belgian government's Energy Transition Fund, to investigate the potential contribution of superconducting technologies to the Belgian transmission network and how they can improve the security of electrical supply, deliver an increased renewable energy share for Belgium, and the associated socioeconomic balance. The STERNA 2050 project has been a collaboration between industrial and academic partners. It's run over the last 2 years, and today we're here to present its findings. Today we're going to hear from most of the partners. Firstly, we're going to hear from Daniel at 3E, who led the characterization of the green power plant of Europe. Then we're going to hear from Dirk, Ricardo, and Hadis from KU Leuven, who've completed an assessment of the potential transmission technologies. Alan from Supernode is then going to present on the characterization and impact assessment of superconducting systems. And finally, Bernardo from DEME will present on the installation and lifetime integrity of the superconducting system. Before I hand over to Daniel, I'd just like to discuss how we'll run today's session. We will be recording the session so it can be made available afterwards. And we're inviting people to use the question and answer function within Teams so that they can pose any questions. And we will answer those after the webinar and publish the answers along with the webinar at a later date. Without any further ado, I'm going to hand over to Daniel from 3. Thank you.
Good afternoon, everyone, and thank you for joining us today. My name is Daniele D'Ambrosio, and I'm the project manager at 3 for the STERNA project. What I'll be presenting to you today is our work on modeling offshore wind development in the North Sea, looking all the way out to 2050. So as you can imagine, looking that far into the future comes with a lot of uncertainty. So we took a scenario-based approach, which I'll explain in just a moment. So let's dive in. But first, let me start with some context. As you know, highly ambitious targets have been set for offshore wind in the North Sea, which is really set to become the powerhouse of European wind energy. Specifically, under the Ostend Declaration, North Sea countries pledged to reach 120 gigawatts of installed capacity by 2030 and 300 gigawatts by 2050. And to put that into perspective, as of last year, we had about 30 gigawatts installed. So here we are talking about a 4-fold increase by 2030 and a 10-fold by 2050. And of course, the scale of development raises some critical questions. For instance, on what future grid requirements are going to look like and what levels of power production we can realistically expect from this massive offshore build-out. And these are exactly the questions we set out to answer in STERNA by providing accurate modeling of expected power production. Now, these massive development plans come, of course, with a great deal of uncertainty due to the long-term horizon and the inherent challenges of offshore wind development. And to deal with that, we adopted a scenario-based approach. We started by creating a comprehensive mapping of all existing and future construction areas, of which you can see an example here. And I want to acknowledge the work of my former colleagues, Mathilde Coppi and Anastasia Dagla on this. Then from that mapping, we defined 3 development scenarios based on national targets and designated areas, tracking operational parks per decade up to 2050. In what we defined as the low development scenarios, the installed capacity roughly doubles by 2030, but then sees very limited expansion afterwards. Then we had an expected scenario, which we consider the most likely and shows much stronger growth, particularly in the UK, Germany, and the Netherlands. And finally, the highest development scenario, which assumes that all planned areas plus additional zones from marine special plants gets developed to be able to reach the 300 gigawatt target by 2050. Now, just one quick remark before we go deeper. This analysis was based on conditions existing at the beginning of 2024. Since then, several North Sea countries have had elections and global conditions have shifted considerably. So keep that context in mind. Now, let's deep dive into how we actually converted these scenarios into actual power production estimates, including the effects wake losses from neighboring parks. And our approach starts with wind resource modeling using 3 virtual wet mass technology, which is a state-of-the-art hindcast method that can simulate historical wind conditions at any offshore site in the North Sea. It is driven by ERA5 reanalysis data, which are downscaled using the WRF weather prediction model combined with a deep learning approach. And then microscale modeling and calibration with available measurements in the North Sea ensure that simulated data aligns with real-world observations. Then the wind resource data is fed into our wind farm model, which needs turbines location and their power curves. And we compiled these from public dataset for existing farms, and we generated layouts for future farms based on our scenario mapping. Now here, the central piece of our methodology is the wake modeling. We use PyWake to implement engineering wake models with which we can calculate both internal wakes within farms and external wakes from neighboring parks to get turbine level power time series. Then we went on to validate our approach. We first applied it to the Belgian and Dutch cluster at the edge of the Belgian eastern zone, comparing our simulated production against historical ENSOI data for the Belwind wind farm in 2021. As you can see, we achieved a highly correlated production, confirming that our methodology well captured the real-time series power generation, including internal and external wake effect. We also compared capacity factors across all Belgian Eastern Zone wind farms, which shows a generally good agreement, though our approach tends to overestimate by about 3 to 5 percentage points on average. But this was expected given the simplified physics in engineering wake models, the absence of global blockage effects, and also the likely underestimation of availability and electrical losses. But what's important here is that the temporal variability, which is what really matters for grid planning, is captured quite well. Once validated the methodology, we extended our approach to simulate future wind parks that haven't been built yet. For this, we had first to assume what turbine technology would be deployed, extrapolating from current trends for both fixed bottom and floating offshore installations. And then we also created realistic layouts by developing a dedicated tool that generates turbines positions based on each concession area's geometry and its expected capacity. Now, one important assumption we took here is that all existing wind farms will reach end of life by 2050, assuming 25 years of operational period. In reality, repowering will likely happen for those parks, but we simplify that to life extension, keeping existing parks operational through 2050. Now, to be able to run this very expensive simulation, which compute all parks at turbine level in each scenario, we had to limit the computational complexity of our simulations. So we adopted a clustering approach, grouping the North Sea into calculation clusters. Also, to reduce the temporal complexity, we condensed 20 years of wind data from 2000 to 2020 into a single typical meteorological year for each cluster. And the TMY methods essentially selects statistically representative periods on a monthly basis, preserving seasonal patterns, diurnal cycles, and extreme conditions. And we use the same TMY for 2030, 2040, and 2050, which is an important simplification here that doesn't account for potential climate change effect on the wind resource, but at the same time, it gave us a consistent baseline for comparison across the scenario. So let's go to some results now. Here we show the simulated cumulative annual energy production in terawatt hour, broken down by country for what we consider the most likely development scenario. And the key finding here is that in this expected scenario, the cumulative annual production from the North Sea wind parks is likely to exceed 1 petawatt hour by 2050. And we also translated these results into capacity factors by exclusive economic zone. And as expected, as you can see, as expected from our methodology, from the limitation I discussed before and the assumption we've taken, our capacity factors run a bit high, but still they provide very valuable insights into future offshore development patterns. So to wrap up our contribution to STERNA, what we did was we produced annotated maps of offshore wind development in the North Sea up to 2050 based on 3 distinct scenarios. For each scenario, low, expected, and high, we estimated total installed capacity per decade, 2030, 40, and 50. Using our methodology, we computed hourly power production time series at turbine level for a typical meteorological year for every wind park in each computational cluster. And finally, by aggregating all this data, we found that under our expected scenario, annual wind energy production in the North Sea is likely to exceed 1 petawatt hour by 2050. And that's all for me. Thank you.
Thank you very much, Daniel. Now we're going to hand over to Dirk and KU Leuven.
Thank you for all joining in this webinar. I'll talk about the technological options and more in particularly the grid that is required to achieve this massive development that was just presented. Okay, also. So as mentioned, we have very nice goals to aim at, and depending on who you ask, these numbers, they vary. But they're all in the hundreds of gigawatts, but it's not just the offshore wind, there's also onshore that we will develop. And the expectation is that by 2050, we'll have about 1,500 gigawatt of solar. Clearly, if you have offshore wind, they're placed in an inconvenient spot. I mean, there are not a lot of power lines there today. You need to develop a system that connects that. European Commission has put forward that this would be roughly 1.2 trillion euros, I guess, or 1,200 billion. Mostly for distribution, but still a nice 500 billion just for transmission. So it's worthwhile to do it. And if we zoom into the North Sea, and we would have massive transmission available, which is beyond current day capacity, we would see some kind of a spaghetti for my Irish colleagues, especially, but also some 5 gigawatt lines to Ireland, where currently the Irish system has roughly 10 gigawatt of capacity. It's probably difficult to put so many cables. So we need to make a grid, and then we need to put it in. And that would require quite a bit of additional transmission lines to be connected to the grid. Here in this case, I show how many particular 6 gigawatt transmissions you would need between Kiel, which is in Germany, and between the border between Belgium and France. This is not a marginal upgrade. This is a fundamental upgrade of the system. And this will require us to thinking from line by line investments into a multi-gigawatt corridor investment. And for that, we focused on a number of things within this project. We looked at what kind of technologies would be available. We looked at how to integrate those new technologies also in computational tools to actually consider them. And then we tried to figure out how many gigawatt kilometers of grids we would need in the offshore environment. And I'll give the floor to my colleague Ricardo, who will discuss the first two parts, and then Hatice will do the second. Ricardo, please.
Okay. Hello, everyone. Thank you for your introduction. I'm a PhD researcher at KU Leuven, and I will present the first logical step after we decided that we need, and we calculate we need more grids, but now we need to identify which technology are we going to use to develop this grid. So the first part, we developed a high-level review of the transmission technologies that are capable of delivering multi-gigawatt capacity. And the goal of this first part was to create a clear classification framework that allows system planners to quickly understand which are the trade-offs. For this, we define a set of high-level KPIs, such as the one you can see on screen, such as capacity per circuit, experience, auxiliary equipment. And with this classification, it makes it much easier to identify, compare the technologies in a consistent manner. One of the main outcomes of this review was a summarizing table that shows how the KPIs per technology are evaluated. This was part of a conference paper last year, and it serves as a practical reference to understand which technologies are better suited for these multi-gigawatt transmission corridors. Now, the next step was to model the superconducting cables. And for the modeling part, we use power model of AC/DC, but what is power model of AC/DC in the first place? This is an open source optimization framework that allows us to perform optimal power flow simulations for AC and DC grids, and has several functionalities, such as transmission expansion planning and redispatch optimization, and serves as a backbone for other extension tools. However, this tool does not have any model for superconducting cable. And the main reason for that is that the superconducting cables have a very low resistance, almost zero. And this is very useful when you want to transport practically several hundreds of gigawatts or megawatts. But when you're trying to calculate in existing tools, then you reach a problem because then you have a division by zero. So this introduces numerical challenges. To solve this, we develop an extension of power models that includes the DC superconducting cables that, instead of being a traditional branch, is modeled as a power injection. And this is done by adding a set of extra constraints, which models the cooling station of the cable as active and reactive loads into the exit side of the converter. So this keeps the model numerically stable, while still representing the operational impact of having a superconducting cable capable of transporting several gigawatts of power. Thank you, and I'll give you the floor to Hatice.
Thank you, Ricardo. As Dirk mentioned earlier, in the second part of our research, we focused on the merits of different system configurations and cable technologies, how they would impact transmission needs to bring the power from future offshore to onshore, and also to the effect of meshing and redundancy. Thinking about the 300 gigawatt offshore generation by 2050, if we want to bring this power only by using 1 gigawatt or 2 gigawatt cables, our analysis shows that we need more than 24,000 gigawatt kilometer connections, cable connections from offshore to onshore. And in addition to this, we need within cluster wind farm to wind farm connections, which would be also about 6,000 kilometers in distance. In comparison to this, if we would be looking for larger size clusters, fewer clusters, but then use larger capacity connections with superconducting cables from offshore to onshore, we see a significant improvement in this gigawatt kilometer requirements, drops down to around 6,000 gigawatt kilometers for onshore connections. But this also means fewer clusters also implies that you have larger clusters, so then larger interconnections or intraconnections between wind farms, but with relatively lower capacity cables, which overall imply a better strategy based on our analysis. But these numbers are only for offshore connections. We would also need inland reinforcements to bring this power to onshore grid. Then these numbers even go higher. So the approach, briefly, the approach we utilized for reaching these results was to cluster the offshore wind farms, connect them from offshore to onshore, not only by taking into account the distance, but also the installed capacity, and then look into the distances for within cluster connections. This proved taking into account distance and capacity proved more useful than just looking into distance. So this was briefly what I wanted to tell. Now I will let Dirk conclude.
Okay. I'll summarize quickly for what the grid aspects. What we have seen is that as transmission lines become bigger in size and more heavy, the capacity increases. As expected, HVDC becomes the key technology, but also superconductivity becomes interesting because you will be able to go beyond the multiple gigawatt scale. There's still some work to be done, but it would create significant value. We also see that it is possible. It's nice because we needed it afterwards to upgrade our power flow tools to incorporate superconductivity. So we did that. It's an open source tool, so if you want to use it, you can. And then we did a greenfield study using the Belgian offshore wind farm region. We didn't want to redo the work of Elia, and we're not going to do it. It's not that we did grid planning specifically. We were more investigating the comparison between topologies and choices that you could make and a larger system. Of course, clustering brings significant benefit. It's necessary to get that done. That means that you would have offshore energy islands or equivalent that join the power, and it would allow us to get a tailored and larger capacity onshore offshore connections, which that would then use that technology that we just mentioned. That would lead to higher use of these lines and a decreased operational cost. And of course, we also looked at reliability and redundancy in not at the full system, at a smaller system. And again, there, clustering and bringing together wind farms brings substantial benefits. We also looked at how many DC breakers you would need and whether you would need DC breakers for everything. And there is a benefit to use what we call symmetrical preventive DC side decoupling, meaning that you run the system open until something happens and then close with switches rather than with DC breakers. And that would also be beneficial, something we found out. And with that, I think we can hand over the floor to Alan, if I'm correct.
Good. Thanks, Dirk. Over to you, Alan.
Thank you very much, Dirk. Thank you, Peter. So I will attempt to condense the Supernode's contribution to the project in these next few slides. It's been an exhaustive piece of work. It's been a quite detailed piece of work. So it's quite a high level view. As the previous speakers have spoken to, they've the research and the analysis zeroes in on superconductivity for enabling these targets to be met potentially. So that's where Supernode fits into this project. We are superconducting cable development people. We are experts in the field of superconducting. So in the first instance, to explain briefly what a superconductor cable is, to those of you who may not know, specifically in the scope of this project, we speak to DC being one of the key enablers here. So this difference between superconducting cables and traditional cables is this key statement: zero electrical resistance, no resistive losses. And in the kind of large, very, very large power densities that we've just been speaking to, this is where we need to get to be able to achieve multi-gigawatt capacity within single cables. So that being said, the analysis by the KU Leuven team shows that if we were to do it traditionally, there will be many, many connections, many kilometers. We have the ability within our technology to deliver this level of functionality in a smaller footprint. And that's the key message here is typically we would need an extremely small space compared to traditional methods to deliver the same level of power capacity. So briefly then, the superconducting cable itself, a liquid nitrogen core around contained within a smooth bore polymer cryostat, which is proprietary to Supernode. We are the world first to develop this technology, wrapped with high temperature superconducting tapes, encapsulated then in layers of insulation and armoring and electrical insulation and thermal insulation. But this is state of the art and innovative technology that has been developed by us here in Supernode. So the Supernode cryostat technology itself, where we are better is here. The performance profile in this screen grab from a model output shows that we have quite smooth current flows within the fluid as compared to traditional methods which rely on metal cryostats, which have inherent problems, which have been an issue for superconducting cables in the past. Again, the smooth bore polymer cryostat delivers this level of functionality, and we can see an order of magnitude of gains of performance from our technology compared to what has previously been available. The cable itself is just one part of the solution. The ability to join the cable and the ability then to work with the liquid nitrogen that is a necessity for superconducting are fundamentals to this. They formed aspects of this project as sub-work packages. So the cable jointing method and the marine cooling and pumping pod or CPP. So what the CPP would look like from a size perspective, how often they would be needed, and the rigid cable joint, how would it manifest, how would it look, and how then would it be installable underwater, and that connectivity and handling and so on. What we've seen from the work that we've done, again, is the ability to go much further than is currently available than the current state of the art. So less stations, further distances, greater power quantities, which are speaking directly to the problem as defined in the previous sections. Our key headings that we looked at from our work packages was operational, economic, environmental, and finally then the geopolitical and supply chain aspects of this. Again, we're just touching on it briefly. From an operational impact perspective, operationally, electrically, there are zero resistive losses when using a superconducting cable compared to a traditional cable. The cooling power consumption, so the amount of energy needed to cool the cable, is still far less than the actual quantity of losses that would be seen in a traditional cable. And the high power capacity, so being able to achieve multiple gigawatts inside one small diameter cable compared to traditional methods and what would be required traditionally. Supernode exists here where the orange dashed line is on screen, and the traditional methods are all of the ramp up curves on the edge of the graph. So still comparatively from a modeling perspective, huge gains and huge distances between what is nominal for Supernode and what is significant losses with traditional solutions. Again, looking at what can be done within the footprint. So the conventional cables, numbers of circuits, quantities of gigawatts, indicated voltages, none of these are particularly favorable when looking at the same problem from a superconducting perspective, specifically Supernode. Then things can be done at much lower voltages, which are friendly from downstream equipment, ancillary equipment, switchgear, circuit breakers, turbines. All of these things are, we would prefer to work in a lower voltage envelope. When we get into 5, 6, and 8 gigawatts, we can still achieve this level of power transmission with relatively few cables compared to traditional. So orders of magnitudes of benefits from a superconducting approach as compared to a traditional approach. So quickly then, the combined cooling pumping stations would be approximately 25 kilometers apart. Again, from a modeling perspective, the realities would be slightly more or slightly less depending on geography and the needs of an actual project. But that value of 25 kilometers, again, is significantly more than what is currently achievable using state-of-the-art superconducting cables as they currently exist. The infrastructure is defined at intervals. This is nothing new. We need to do things at different distances. The supernode approach allows for greater distances between those pieces of infrastructure. From an economic impact perspective then, the economic advantages are quite numerous. They're easy to see when you get into this. They're listed here on the left. So scalable at negligible weight and cable diameter cost increases. So if I want to put more gigawatts down through the cable, I don't need a bigger cable and I don't necessarily need more cables. I add more superconducting materials to the same cable. So that's one of the key differences. The superconducting tapes can be seen in the image on the bottom, wrapped in a very traditional way, in a way very similar and aligned to traditional cables. We would just simply add more capacity to the cable. More power transmission needs more HTS tapes, not more cables. HTS superconducting cables are significantly lighter than traditional cables. Within the superconducting cable is a vacuum. It's not contained with solid layers of insulating plastic. It's a vacuum environment. It's just hollow, and as such, it's obviously significantly lighter. Zero electrical losses. Existing cable deployment technology and techniques can be utilized here. So the same types of ships, the same types of cable handling methodologies as will be seen later. Lower operating voltage, which has a direct impact on the infrastructure. The upstream and downstream infrastructure working at lower voltages is a lower price point for the equipment. So it's cost effective at scale. More gigawatts is better. When we start getting into those scaling opportunities, we can see clear economic advantages compared to what is currently available. So when looking at large wind farm turbine arrays at sea, then the strings of wind turbines have to be connected together. Infrastructure is needed, highways are needed to guide the electricity, guide the power to shore where it's needed. This is traditionally done with collector stations, and you can see conventional, very briefly, conventional stations compared to what would look like from a superconducting perspective. And again, it's the same message. It's a smaller footprint, less hardware, less needs, less demands, less intensity and less cost. So superconducting takes up a smaller footprint to achieve so much more, globally speaking, from an economic perspective. So from an environmental impact perspective, and again, trying to briefly condense it, we simply take up less footprint. So the installation on the seabed, the installation of the infrastructure, installation as we transition from sea to shore, all of that simply takes up less space. Smaller cable corridors are required. Fundamentally, a superconducting cable has lower EMF, quite significantly lower EMF. Minimal heat emissions, so wasted energy is at an absolute minimum in a superconducting environment, and minimal environmental impact during the installation and decommissioning. So if I'm having to install less equipment by greater distances and smaller footprint equipment, then automatically it's less of an impact on the environment during the installation and commissioning phases. So looking at it then from a material composition perspective, we need less materials to create similar capabilities in superconducting cables. So a superconducting cable requires approximately 3 tons per kilometer, as opposed to 22.75 tons per kilometer for a conventional cable. So it's somewhere around approximately, depending on the spec, 86% reduction in copper requirement for an equivalent superconducting cable. So a significantly reduced copper demand is better for the environment. And notably then, it's also 48% approximately, again, depending on specification, lighter than traditional cable. So it would cost less in fuel for the ship to transport the same length of cable, or we can put more cable in the ship and the ship can be at sea longer duration. Either way, economic savings, directly visible economic savings from using superconducting technology as opposed to traditional cables. This is a very, very high level overview of the low level mineral content in the superconducting cable, so I won't linger too long. It's just to show on screen that its energy intensity is favorable compared to traditional cables, and the footprint again of what's needed, which goes into it. So quite an extensive piece of information and work package to back this up, this single slide, and not enough time to really get into it in a meaningful way today. So finally then, the geopolitical and supply chain impacts. So as mentioned by Daniele earlier on, the geopolitical landscape has changed extensively in the last 2 years. Superconducting speaks to that directly in how the materials are arrived at and where they're sourced from. So again, a high level view of that particular vantage point. So supply chain vulnerabilities require strategic diversification, and I think that's understood by all. With superconducting cables, you're not taking from the existing high-powered cable supply chain. This is new. This is separate, and it means that we're less reliant, less dependent, and less problems around that particular aspect of things. So the critical mineral mining is probably the single biggest takeaway from this slide, and that this is obviously something to be watched and something to be protected and spoken to with trade agreements and whatnot. But the critical elements are for sure a concern, but something that can be clearly spoken to and clearly seen in the makeup of a superconducting cable. So finally then, the environmental and operational impact assessment and conventional cables. So very simply, 8 gigawatts would take potentially 4 traditional circuits across 8 cables, and the same could be achieved across 1 circuit and 2 cables from a superconducting perspective. So significantly less effort required to build an equivalent circuit using superconducting technology. And finally then, 34 tons per kilometer. So when I look at the whole cable, not just the copper content, it's 48% lighter than conventional. So previously spoke to just the copper content. This is looking at the whole of the cable, the plastic element, the other material element. So 48% lighter than conventional for like level of functionality. And so finally, our conclusions then from our work packages. So the technical viability of superconducting cable systems compared to traditional cable systems for large-scale offshore wind power transmission, we've spoken to that clearly. Assessed the various impacts and highlighted the benefits of superconducting cable systems in these use cases from an operational, environmental, and technical over the traditional cables and systems that are currently in place. We've shown that there is less demand on existing supply chain when using superconducting cables, and the superconducting cables for offshore wind farms offer a lower carbon footprint solution with far less material needs for equivalent power transmission. So those are our key takeaways from the STERNA 2050 project. So thank you very much.
Very good. Thank you, Alan. Now we're going to hand over to Bernardo from DEME.
Yes, good afternoon, everyone, and thank you for joining this webinar. My name is Bernardo Gianelli, and I'm an expert engineer in DEME. And in this project, I contributed, and what we did was we leveraged on our experience as a contractor to verify the possibility to install this cable and the whole cable system that Alan just described in the previous part of the presentation. So going a bit more in detail, what we did, first of all, we took in the proposed design, and we review it when we familiarize with it. And in a second instance, we described how we would install it at this stage. So we prepared a work method statement describing the installation phases and even drafting drawings of how we forecast to install it and the equipment we would need to install it. Secondly, we work into the installation analysis of the installation itself from in a few different scenarios of how to install the cables, how to install the other components that are needed as the cooling and pumping pods that needs to be installed periodically to cool down the nitrogen, and also how to bury the cable and how to install to pull in the cable at the substation and onshore. Finally, we combined the results that we achieved in a risk analysis. So, if you can see, this is the structure that was just described. And the first things we did, we compared this structure and these properties with what we typically do for installation offshore and what we need in terms of mechanical properties of the cable. As you can see in this table, MBR stands for minimum bending radius. So the cable has sufficient already bending radius which is compatible with our requirements. Tension limit as well, which is compatible with our requirement. But its specific gravity, so its density, was not the original version, which is, let's say, a typical design for more for a land installation, was not dense and didn't have a specific gravity high enough to be installed offshore according to our requirements. So what we did, together with Supernode and agreeing on the different modification, we propose an improved design of the external layers of the cable. So in a certain sense, we complemented the design in order to reach a specific gravity of 1.9. This also grants additional protection of the cable, and it's not presented here, but we also verified that the crash loads that we would need to install the cable are respected due to this improvement. Afterwards, as I was saying, we developed specific method statements for the different phases that are needed for the installation of the cable and the installation of the different structures offshore, mainly the CPPs. To do this, we use the vessels that we are familiar with, and of course, this has a high project-specific dependence. So also in this case, we forecasted different scenarios of installation depth, mainly focusing on the south and central part of the North Sea, because we estimated that to be the first potential area where to focus upon. And this is further presented in our report. Of course, in the case of depending on the water depth, we might need very large installation vessels to install the CPPs as is represented here. As I was saying, next phase was the verification of the burial of the cable and the installation with the software that is a common industry standard in Orcaflex. So regarding the installation, one parameter that we think it's important to highlight is that we believe these assets to be especially critical and because of the amount of power which is carried. So a specific cable burial risk assessment shall be performed by project, but we forecasted that higher depth of installation might be needed, and so this needs further attention. But we believe that with our current means, with some improvement, we can reach such higher depth. The cable also has a rather high bending stiffness, and this might also present some complications, but as well we believe that that's something that needs to be refined, but it's also compatible with the existing burial tools. For the installation analysis, as you can see in these two videos, we presented for the cable installation offshore, 2 scenarios were simulated, and the main, let's say, at this stage of the characterization, the main limitation for the operability is the possibility to compress the cable, but in general, we believe that phase to be feasible. More complex is to study even the pooling analysis at the offshore and onshore, because the specific plug and play terminations is to be further developed, and this will be performed at a later stage. So, what are our main risk evaluated from this from the analysis? I briefly explained that we see at this point. The first one is associated with the cable design. So the analysis showed that the installation is feasible, as I was saying, focused on the southern and central North Sea. On the other way around, the mechanical properties are estimated on, let's say, in the base of simulation and of material properties that needs to be validated. Also, because this design, as shown previously, as something which is different from normal cable, is a pipe-in-pipe design where the nitrogen is flowing inside. Of course, not at the time of installation, but that pipe would be empty. But still, it's somewhat different to what we are used to. And its compression responses and behavior needs to be validated through real mechanical testing, as it's also the case for conventional cables. The risk associated with the joints and termination design. In this case, the joints of the cable that were presented also by Alan needs to combine electrical stresses, circulation of liquid nitrogen, and vacuum for the thermal insulation. So this technology exists separately, but needs to be combined. In this case, needs to be combined, and so uncertainty still exists in the actual TRL level to be reached at this moment. So, and also potential changes in the installation that we forecast might occur. For the CPPs, so for the cooling and pumping pods, as I said, this would require the somewhat large vessels and add on to the installation complexity with an additional asset that needs to be installed further than the cable. And so also this needs attention, even though it's not believed to be critical or unfeasible, but will add on to the cost. And lastly, the risk associated with the burial and protection of the asset. As I was saying, considering the amount of power, this needs to be taken into consideration, because a failure in this kind of system would be even more critical than conventional power cable. To summarize what was exposed, in terms of technical feasibility, we deem it to be preliminary feasible, but again, further mechanical characterization needs to happen and needs to test the real cables. There is an increase in installation complexity due to the joint that needs to be installed, and due to the higher amount of joint that needs to be installed, and due to the cooling and pumping post installation as well. So the cost and duration can be more complex and long. For the preferred installation method, somewhat similar to existing cables, we propose hybrid trenchers depending on the soil conditions, and for the installation close to shore, horizontal directional drilling or trenching are both feasible. And again, the further work is now lying in further characterization of the cable mechanical properties and testing, somewhat similarly again to what is done for conventional cable. The qualification can be quite long and many different tests needs to be performed, but in this case, even a bit more of uncertainty exists in the mechanical properties. And of course, when it's done, finalization of installation procedure for the cables and for the pre-terminated ends at onshore and offshore. Onshore and for the pull-in at landfall.
Thank you, Bernardo. And I'd just like to wrap up briefly. I'd like to say thank you for all the presenters presenting on the project today, and for all of the partners for their valuable contributions. It's been a great project to be part of. I'd like to again thank the Belgian government's Energy Transition Fund for funding this project. I think it's been insightful. It's shown there are many potential benefits to pursuing these technologies, how it can be done. We've heard from 3E about the huge potential renewable power source that is the North Sea, and what we can potentially harvest there. We've heard from Kay Lubin about how we might land the power, the challenges with the current technology, how we need to move to multi-gigawatt transmission networks, and how they might be made up. Alan's talked about the makeup of the superconducting cables themselves, the benefits they bring. And then we've heard from Bernardo Ademe about the feasibility of deploying this technology at sea, how it can be done, the equipment, the different methodologies that are there. Finally, on behalf of all the project partners, I'd like to thank everyone for attending today, giving us the opportunity to disseminate what we've learned throughout the project. I hope you found it insightful, and I'd please like you to submit any questions you might have using the function on Teams. We will be providing the recording of the webinar and the output from the project. We will be publicizing that afterwards. But thank you very much, everybody.